Welcome back, listeners, to The Deep Dive. Today, we're diving into a topic that really pushes the boundaries of what we thought large language models could do. Imagine if your favorite software, something truly complex, could not only learn from new data, but also figure out the absolute best way to learn it. What if it could generate its own optimal training material and then continuously improve itself, evolving its own understanding, all without any human programmer having to step in and manually tweak things? That's not just a sci-fi dream anymore, it's precisely what we're here to unpack today. As always, we'll focus intently on the technical details and implications of the technology we discuss, steering clear of broader societal or ethical discussions, keeping our lens fixed on the engineering and algorithmic breakthroughs. For those of you eager to stay updated on the latest AI and ML research papers, remember to visit our webpage, which is always linked conveniently in the bio. Today, we are taking a deep dive into a fascinating new framework from MIT called Self-Adapting LLMs, or SEAL. Now, this isn't just your run-of-the-mill fine-tuning, which we hear so much about these days. This is about language models learning to self-edit and, critically, to self-optimize their own learning process. It's a profound shift in how these massive models can evolve and refine themselves. Our mission for this deep dive is clear. We're going to meticulously explore the ingenious technical mechanisms behind SEAL. We want to help you truly grasp its implications for how LLMs can evolve, and we'll discuss the promising results they've achieved in crucial tasks like knowledge incorporation and few-shot generalization. We'll be laser-focused on the technical architecture, its inherent capabilities, and the future technical challenges it still faces. Our goal is to get you thoroughly well-versed in these cutting-edge technical details, and perhaps spark some thoughts about what this might mean for the future of autonomous AI development. To really get a handle on this, let's unpack it with an analogy that might make it click. Think of a human student, say a really bright one, preparing for a highly complex exam, maybe in something like advanced quantum mechanics or, organic chemistry. They don't just passively read textbooks cover to cover, do they? That's not how truly effective deep learning works. Instead, they actively engage with the material. They might take intricate notes, rephrase dense information in their own words, perhaps draw elaborate diagrams to visualize abstract concepts, or even create their own challenging practice questions to test their understanding. What they're doing is fundamentally restructuring the raw information in a way that helps them learn and retain it better, making it much easier to recall and apply that knowledge later. The self-edit concept in SEAL is incredibly similar to that. It's an LLM generating its own notes or learning directives, but in an optimal format specifically for itself to facilitate its own internal learning.
That analogy perfectly sets the stage because it highlights a critical limitation of traditional LLMs. What's fascinating here is how conventional LLMs are typically quite static after their initial, often monumental, pre-training phase. Once these models are released, adapting them to new, evolving tasks, integrating truly fresh, novel knowledge, or even helping them master new skills becomes a significant technical hurdle. Why is this? Primarily because you're often severely limited by the availability of high-quality, task-specific data. And even when that data is available, these models typically consume it as is for fine-tuning or in-context learning.
Right, they just take what they're given.
Exactly. Which raises an important question for anyone building these systems. If the provided data isn't in an optimal format for the model's internal learning mechanisms, or if there simply isn't enough of it, how can an LLM truly develop bespoke, efficient strategies for learning from it? That's precisely the core problem SEAL aims to solve, enabling a model to essentially optimize its own learning input and process. It's a move from passive consumption to active internal data curation.
That's a powerful distinction you just made from passive consumption to active internal curation. It really underscores the paradigm shift SEAL represents. So let's dive into section 1 and truly explore this core idea of self-adapting LLMs, or SEAL. What exactly is the fundamental problem SEAL is trying to overcome in the first place?
The fundamental problem, as we've touched upon, is that current LLMs, despite their immense power derived from being pre-trained on, petabytes of text data, are largely static artifacts once that initial training is complete. Think of them as incredibly powerful, but ultimately fixed knowledge bases. They're like encyclopedias printed on stone tablets, vast knowledge, but incredibly difficult to update or adapt efficiently.
To a rapidly changing world, yeah.
Precisely. Adapting these models to new, specific tasks Integrating novel factual knowledge or even helping them master new reasoning skills is profoundly challenging for a couple of key reasons. First, there's the limited availability of truly task-specific data. If you want a model to become an expert in a niche domain, getting vast, perfectly curated data sets for fine-tuning is often prohibitive, expensive, or just impossible. Second, and crucially, these models consume data as is,
Mm.
whether it's through supervised fine-tuning, which involves gradient-based updates on provided data sets, or in-context learning, where they infer from examples presented directly in the prompt. They generally just take the data exactly as it's given. But this provided data may not always be in the most optimal format or even the right volume for the most efficient internal learning by the LLM. It's akin to getting a student a giant, unorganized pile of raw research papers and expecting them to instantly internalize everything without ever summarizing, restructuring, or creating their own study guides.
Right, the information might be there, but its format isn't conducive to optimal learning.
Yeah.
So this is where the truly innovative concept of self-edits comes in, which is really the heart of SEAL. It's not just about passively taking in information. SEAL empowers LLMs to actually generate their own self-edits. Could you elaborate on what these self-edits actually are from a technical perspective? What forms do they take and what do they allow the model to do?
Absolutely. From a technical standpoint, these self-edits are precisely what they sound like. Natural language instructions generated by the LLM itself. They are explicit directives that the model formulates for its own learning process. What makes them so powerful is their incredible versatility and granular control. They aren't just generic commands. For instance, a self-edit can specify precisely how to restructure information. Imagine the model reading a dense scientific paper. A self-edit might instruct itself to summarize the key findings into bullet points or extract all causal relationships between variables. Or even rephrase this complex paragraph into 5 simple sentences, highlighting the core implications. This is the model creating its own internal learning materials. Beyond data restructuring, self-edits can also dictate which optimization hyperparameters to use for subsequent training. This is a game changer.
Early, so it tunes itself.
Pretty much. Instead of a human manually tuning a learning rate or deciding on the number of training epochs, the model could generate an edit like set learning rate to 1E5, train for 3 epochs, and use cross-entropy loss over output tokens only. This allows the model to dynamically adjust its training regimen based on the specific learning tasks it faces. And crucially, self-edits can invoke various tools for data augmentation. We'll get into this more in the few-shot learning application, but imagine the model identifying that for a visual reasoning task, it needs more diverse training examples. A self-edit could be apply random rotations and flips to all input images for augmentation. This is the model taking control of its own training data generation pipeline. The key technical outcome here is that these self-edits then lead to persistent weight updates through supervised fine-tuning, or SFT.
Okay, persistent updates. That's the key difference from just a in-context learning.
Exactly. This is critical because it means the model is not just temporarily adapting its behavior for a single query, it's making lasting structural changes to its own parameters. It's fundamentally rewriting its own memories and refining its internal capabilities in a truly autonomous way.
That distinction, persistent weight updates, is indeed profound. It's not just learning from examples, it's changing its internal state. So this begs the question. How does the model learn how to generate these effective self-edits in the first place? There must be some overarching mechanism guiding this. The paper points to an outer reinforcement learning loop, highlighted conceptually in Figure 1. Can you walk us through that and maybe shed some light on the deeper implications of a model generating directives for its own learning?
Absolutely. At a high level, SEAL employs an outer reinforcement learning, or RL loop, that drives this entire self-adaptation process. Conceptually, think of it as a continuous feedback system, a sort of meta-learning loop. In each iteration of this RL loop, the language model acts as an agent. Its action is to generate a set of candidate self-edits. These aren't random, they're sampled from its current policy, which is essentially its learned strategy for generating beneficial learning directives. Once these edits are generated, they are immediately applied to update the model's weights through an inner fine-tuning process. This updated model then has its performance meticulously evaluated on a specific downstream task. This performance is then quantified and converted into a crucial reward signal. This reward signal is the feedback mechanism. It's fed back into the system to improve the self-edit generation policy for the next iteration. This creates a continuous, self-improving feedback loop where the model consistently refines its ability to generate increasingly effective learning instructions for itself. The key differentiator here, as the paper highlights, is that unlike many prior methods that might rely on separate adaptation modules or auxiliary networks to guide learning, SEAL directly uses the model's own generation to parameterize and control its adaptation.
So the model tells itself how to learn better.
Exactly.
Right.
Rather than relying on an external trainer or a separate static module, this implies a fascinating level of internal awareness. For a model to effectively suggest modifications to its own learning process, it implicitly needs to understand its own learning dynamics well enough to propose truly effective changes. This isn't just about regurgitating facts, it's about reasoning over its own internal architecture and optimization landscape. It suggests that the model's internal representation somehow encodes not just explicit knowledge, but also meta-knowledge about how that knowledge is best acquired and how its parameters evolve.
Like a kind of introspection.
Yeah,
Yeah.
exactly. Where the model is not just performing a task, but also optimizing the process of performing that task. It's like a student who not only learns calculus, but also figures out the most efficient way for them to learn calculus.
That's a truly profound design. It suggests a kind of metacognition for LLMs. But let's dig into the purely technical implications of this self-edit generation. It's not just about generating coherent text, it's about generating directives for its own learning. What does that imply about the model's internal representation, and what specific technical mechanisms do you think are at play that allow for this level of self-reflection? The paper doesn't explicitly detail this, but it's a huge underlying question.
You've hit on a fascinating and somewhat speculative area that the paper touches on implicitly. For an LLM to generate truly effective learning directives for itself, it can't just be generating plausible-sounding language. It must possess some internal representation that correlates specific linguistic structures in the self-edit with predictable effect on its own internal parameters and subsequent performance. This implies a few things. Firstly, the model's internal state must encode a kind of model of its own learning. It has to understand, for example, that summarizing a passage will lead to a more concise representation in its weights, or that increasing the learning rate might speed up adaptation but risk overfitting. This isn't necessarily explicit symbolic knowledge like, if learning rate equals high, then overfitting risky high, but rather an implicit learned mapping within its vast parameter space. The activation patterns might effectively represent these relationships. Secondly, it suggests the model has learned a sophisticated causal understanding of its own internal workings. It knows that applying this type of self-edit, say, generating implications to this kind of input data, like a passage for knowledge incorporation, will result in that desired performance outcome, like better QA accuracy after fine-tuning. This learned causality, which is purely derived from the RL feedback, is remarkable. The specific mechanisms would likely involve complex interplay between its attention heads, which could be learning to identify which parts of its own internal state or input context are learnable, and its feed-forward networks, which then translate those insights into the token sequences that form the self-edits. It's effectively optimizing its internal compiler for learning. The paper doesn't dive deep into this how because it's still largely a black box in large neural networks, but SEAL's success suggests this meta-level understanding is indeed emerging.
It's incredibly insightful, a model developing a learned causal understanding of its own learning process. All right, that discussion of internal reflection leads us directly into section 2, which is the technical deep dive, how SEAL actually learns to self-adapt. The paper meticulously describes two nested loops, an outer RL loop and an inner update loop. Could you walk us through how these two loops interact in practice, perhaps describing the flow of information between them?
Of course. This nested loop architecture is truly fundamental to SEAL's operation, and understanding its interaction is key to appreciating the framework. We have the outer RL loop, which is the high-level orchestrator. Its primary role is to optimize the process of generating increasingly effective self-edits. Think of it as the strategic planner. In this loop, the model takes an action, which is the generation of a specific self-edit SE sequence. This SE is essentially a natural language program for itself. Following this action, it then waits for the consequences. The consequence is measured by the performance of the updated model on a downstream task. This performance is then quantified and converted into a reward signal. The policy for generating self-edits is then adjusted via reinforcement learning algorithms to maximize this expected reward over many iterations. It's continuously learning to craft better learning instructions.
Okay, and nested inside that.
Nested within this is the inner update loop. This is where the actual parameter modification magic happens. The self-edit that was just generated by the outer loop is fed into this inner loop. The model's current parameters, typically denoted as AE theta, are updated via supervised fine-tuning SFT, based on the content and directives specified in that self-edit. This process yields new, updated parameters, beta prime. So, to define the variables clearly, C represents the context, which could be a passage of text for knowledge incorporation or a few-shot demonstration for generalization, and tau is the specific downstream evaluation task, like a set of questions or a particular query input. The reward R is directly based on the performance of that ELMA, the updated model on the task. This creates a tight, iterative feedback mechanism where the model is constantly refining its ability to generate beneficial self-edits, closing the loop.
That clarifies the mechanics beautifully. So the performance of the updated model feeds back to teach the initial model how to generate better updates. But this brings up a really significant technical challenge: the reward signal. The paper points out that the reward for a self-edit depends on the model's updated parameters, which makes it non-differentiable with respect to the initial lay that generated the self-edit. Plus, previous state, action, reward triples can become stale. For listeners who might not be deep into the calculus of machine learning, when you say non-differentiable, could you give a quick intuition? Is it like trying to teach a robot to tie a shoelace where it either succeeds or fails, but you can't get smooth, continuous feedback on how close it was to success with each tiny movement?
That's a great analogy. You've precisely captured the intuition. In machine learning, for us to use gradient descent, the backbone of how neural networks learn, we need to be able to calculate a gradient, which is essentially the slope of the error function. This slope tells us which way to adjust our parameters to reduce the error. If a function is differentiable, it means we can calculate this smooth slope everywhere.
Okay.
But when a reward signal is non-differentiable, it's like your shoelace tying robot. The robot either successfully ties the lace, reward, or fails, reward equals 0. There's no continuous "how close was it" signal that gives us a gentle slope. It's a sudden jump from 0 to 1. You can't calculate a smooth gradient across that jump. This makes it impossible to directly backpropagate the reward through the entire fine-tuning process to update the self-edit generation policy. It's like trying to navigate a mountain in dense fog where you only get feedback when you either reach the summit or fall into a chasm.
Right, got it. And the staleness problem.
Add to this the staleness problem. The model's parameters are constantly changing with each update. A self-edit that was good for 8 at time t might be completely suboptimal or irrelevant for 8 at time top plus 1. This can lead to inefficient or unstable training if not addressed.
So how do the researchers specifically address this complex reward signal challenge?
The solution they adopted, which is quite clever in its simplicity, is called RESTM, standing for Rejection Sampling plus SFT. It's an on-policy approach, meaning that the data used for training the policy is always collected from the current version of the policy. This inherently avoids the staleness issue because you're always working with the most up-to-date model. They found this to be a much simpler and more stable method compared to more complex on-policy methods like GRPO or PPO, which tend to be more sensitive to hyperparameter tuning and stability in this specific context.
Okay, RESTM. How does that work conceptually?
You can view RESTM conceptually as an expectation maximization, or EM, procedure. It alternates between two steps. In the E step, expectation step, the system samples candidate self-edits from the current model policy. It essentially generates a variety of potential learning directives based on what it currently believes are good instructions. Then, in the M step, maximization step, it performs supervised fine-tuning, but it reinforces only those samples that receive a positive reward. This is where the rejection sampling aspect comes in. You're essentially filtering out the less effective self-edits.
So you only learn from the good ones.
Precisely. The key simplification that enables this technical approach is the use of a binary reward. The reward R is either 1 if the adaptation using the self-edit improves the model's performance on the task, or 0 otherwise. This binary nature is crucial because it allows the good self-edits to be reinforced directly via supervised fine-tuning. If an edit leads to improvement, it's treated as a positive example for training the self-edit generation policy. If it doesn't, it's effectively ignored or given a 0 gradient, contributing nothing to the policy update. This SFT on good self-edits approach elegantly sidesteps the non-differentiability by only learning from the successful instances, making the training much more stable and effective. It's like only learning from your successful shoelace ties, ignoring the failed attempts when trying to figure out what worked.
That's a much clearer intuition, thank you. So the model learns by absorbing its own direct successes and failures in generating learning directives, focusing on what works. Now, the current implementation of SEAL uses a single model to both generate and learn from these self-edits. But the paper also touches on the potential for a teacher-student formulation, where these roles are decoupled. What's fascinating here is the potential for a separate teacher model to generate edits, and a student model to update using them. This raises an important question. What are the potential technical benefits or drawbacks of decoupling these roles? Could it lead to more robust or specialized self-adaptation or introduce new complexities?
This is a really interesting technical pathway for future research, and it comes with clear trade-offs. In the current single model setup, the model has to be proficient at both generating effective self-edits and then efficiently learning from them. Decoupling these roles into a teacher and student model could offer several distinct technical benefits. Firstly, specialization. The teacher model could be specifically optimized and trained via RL solely for the purpose of generating highly effective, perhaps even novel learning strategies or data augmentations. It wouldn't be burdened with simultaneously performing the downstream task itself, which could free it up to explore a broader, more creative search space for optimal self-edits.
Okay, so one model gets really good at teaching.
Exactly. And meanwhile, the student model could focus purely on efficient knowledge integration from the teacher's directives without the cognitive overhead of generating those directives. This specialization could theoretically lead to a more robust and refined self-adaptation process for both components. Secondly, scalability and efficiency. You could potentially use a smaller, highly optimized student model that benefits from the insights generated by a much larger, more powerful teacher model.
Ah, interesting.
The teacher, being a meta-learner, might be computationally expensive to train initially, but once it learns an effective policy for generating self-edits, it could quickly guide the adaptation of many student models, perhaps even on resource-constrained devices. This could make deployments more efficient. However, there are significant potential drawbacks and complexities. The primary one is the increased complexity of the training loop itself. Now you have two distinct models to manage, potentially with different architectures, training schedules, and optimization objectives.
Right, more moving parts.
Definitely. The RL objective for the teacher model becomes more indirect, as it's optimizing for the student's performance, which introduces another layer of dependency and potentially more challenging credit assignment. Also, if the teacher model isn't truly robust, or if its learned policy is brittle, it could propagate suboptimal or even harmful self-edits to the student, leading to less effective or even damaging updates. It also raises the question of knowledge transfer. How does the teacher effectively convey complex adaptation strategies to the student? Is it purely through the generated self-edits, or would there need to be other forms of communication?
Good point.
This could introduce additional technical hurdles. Ultimately, while it could lead to more specialized and potentially more robust self-adaptation, it definitely adds layers of technical challenges. It's a classic problem in multi-agent reinforcement learning.
That's a great breakdown of the potential and the complexities of a decoupled approach. It sounds like a promising avenue for future technical exploration, especially regarding that specialization. Now, let's shift gears and look at Section 3, where SEAL really gets to show its muscle, the applications. The paper highlights two key areas: knowledge incorporation and few-shot learning. Let's start with knowledge incorporation. What's the core goal here, and how exactly does SEAL achieve it?
The core goal of knowledge incorporation in this context is to efficiently integrate new factual knowledge into an LLM's weights in a persistent way. This means the knowledge can then be reliably recalled and reasoned over by the model without needing the original passage or external context present during inference. This is absolutely crucial for building models that can truly update their understanding of the world.
Right, so they actually learn it, not just see it.
Exactly. The mechanism, as conceptually illustrated in Figure 2 of the paper, is quite elegant. Given a new passage of text, which acts as the context C for the model, the SEAL model first generates synthetic data. This isn't just any data. It specifically generates implications derived from the content of that passage. For example, if the passage is a new news article about a scientific discovery, the self-edit might instruct the model to generate. List several key implications derived from this content regarding its impact on existing theories.
Okay.
Or, for a historical text, extract 5 undeniable facts about the causes of event X and their consequences. This self-generated content, these implications, then form the high-quality training data for a subsequent supervised fine-tuning SFT update. To make this process efficient and lightweight, especially since the amount of data generated per update might be relatively small, they judiciously use LoRa, or low-rank adapters.
Laura, we hear a lot about that.
Yeah, it's a technique that allows for very efficient fine-tuning by only updating a small, low-rank subset of the model's parameters, making the updates computationally cheaper and less prone to catastrophic forgetting compared to full fine-tuning. Once the model's weights are updated using these self-generated implications, the updated model is then evaluated on questions about the original passage. But here's the crucial part. Without access to the original text during evaluation.
So it has to rely purely on what it learned.
Precisely. The model must rely solely on its newly incorporated internal knowledge. The accuracy on these recall questions then directly defines the reward for the outer RL loop. This entire process trains the model to restructure the passage information in a way that is most effective for its own internal assimilation, essentially teaching itself how to best absorb new facts from raw text. The paper provides a great example, a passage about the Apollo program. After SEAL adapts, the model can accurately answer questions about specific figures like Jerome Wisner, who opposed manned spacecraft flights, without the original passage being in its prompt. It's truly internalizing that knowledge.
That's a very clear explanation of the process. And the results here are pretty compelling, especially when looking at Table 2 and Figure 4 in the paper. They used Quen 2.57b for this task. The baseline of just fine-tuning on the raw passage itself showed negligible gain around 33.5% accuracy compared to 32.7% for the base model, which really underscores the problem SEAL is trying to solve. Raw data isn't always optimally formatted for learning.
Exactly. It just doesn't stick well that way.
But when they introduced synthetic data, even without SEAL's RL-driven self-optimization, there was a boost. The synthetic data generated by the base Quen model reached 39.7%, and GPT 4.1 synthetic data pushed it to 46.3%. Here's where it gets really interesting. SEAL's performance hit 47.0%, notably outperforming GPT 4.1's generated data, despite Quen being a much smaller model. What does that tell us technically about what SEAL is doing that GPT 4.1, for all its might, isn't?
This is indeed a critical finding, and it speaks volumes about the power of meta-learning through RL. The fact that SEAL, using a much smaller model like Quen 2.57d, can generate synthetic data that leads to better knowledge incorporation than data generated by a vastly larger, state-of-the-art general-purpose model like GPT 4.1 is highly significant. Technically, it suggests that SEAL learns a superior strategy for data generation specific to the task of its own weight updates.
Wow, tailored to itself.
Exactly. GPT 4.1, while powerful in generating human-like plausible text, is essentially a generalist. When prompted to generate implications, it produces what a human would consider relevant and coherent implications. But these might not be optimally formatted or structured for the specific purpose of inducing persistent, efficient knowledge assimilation within the particular architecture of the Quen model it's trying to improve. SEAL, on the other hand, through its reinforcement learning loop, is explicitly trained to generate implications that maximize the downstream utility for its own fine-tuning process. It's learning what specific phrasing, what level of detail, what logical flow in the generated data will result in the greatest accuracy on those subsequent recall questions after a LoRa update. This highlights the power of the RL loop in discovering highly effective, bespoke data transformation strategies that even very large general-purpose models, not explicitly trained for this meta-learning objective, might not stumble upon.
Is the difference between being a great writer and being a great tutor for yourself?
Well put. That's exactly it.
That's a fantastic point, is learning to be its own optimal tutor. And it wasn't just in the single passage setting. They also tested a continued pre-training CPT setting with 200 passages, where the model assimilated information from all of them in one run and was then evaluated on nearly 1,000 questions. SEAL again outperformed baselines, achieving 43.8% accuracy. This suggests the learned editing policy generalizes beyond a single isolated adaptation, which is huge for real-world continuous learning.
Absolutely. That generalization is key.
And if you look at Figure 4, which tracks accuracy over RL iterations, SEAL converges remarkably quickly, surpassing GPT 4.1 data in just 2 iterations. That rapid learning of an effective self-edit style is pretty impressive, wouldn't you say?
It absolutely is impressive, and it's a strong indicator of the efficiency and effectiveness of the REST-M training approach. The quick convergence shown in Figure 4 means that SEAL isn't just learning an effective policy, it's learning it fast. This is crucial for practical applications where training time is always a constraint. Moreover, the ability of the self-editing policy to generalize to a continued pre-training setting with 200 passages is a very strong technical validation. This signifies that SEAL isn't just learning to game a specific narrow setup with one passage, it's learning a more fundamental, generalizable method for how to best structure information for its own internal knowledge acquisition across a broader data set.
Right.
This is a crucial step towards models that can continuously learn and update their world model over time from diverse information streams, which is a major long-term goal in AI research, moving away from the static, periodically retrained paradigm. It suggests the learned self-tutoring strategy is robust.
All right, let's move to the second major application, few-shot learning. Here, the goal is for LLMs to generalize to novel tasks after seeing only a very small number of examples. This is often where LLMs struggle most without extensive fine-tuning. How does SEAL tackle this, and what kind of tools are we talking about the model configuring for itself?
In the few-shot learning domain, the challenge is exactly as you described. How do you get an LLM to perform well on a new task with minimal examples? SEAL approaches this by adopting a test-time training, or TTT, protocol. TTT involves adapting model weights temporarily based on the specific input it receives, typically through gradient-based updates on a few provided examples. The standard TTT approach often uses augmentations of few-shot examples or specific optimization settings, but historically, these augmentations and parameters are manually tuned by human experts or rely on heuristic rules, which limits their adaptability.
So SEAL automates that tuning.
Precisely. SEAL's profound innovation here is that it learns to autonomously select these augmentations and optimization settings. The model generates a self-edit that specifies which predefined tools to invoke and precisely how to configure them for a given few-shot problem. These tools are essentially modular functions that can manipulate the data or the training process. For instance, in the context of the abstract and reasoning corpus, or ARC tasks, those visual problems involving grids of colored squares, where the model needs to infer abstract rules for transformations, the self-edit could specify various data augmentations.
Ah, okay, like image manipulations.
Exactly. These might include geometric transformations like rotations, rotate input grid by 90 degrees clockwise, flips, flip along horizontal axis, reflections, transpositions, resizing operations, or even chained and repeated transformations, apply rotation, then resize, then flip. The model essentially decides how to synthesize more diverse training examples from the few it has seen. Beyond data manipulation, the self-edit can also select optimization parameters for the fine-tuning. This includes things like learning rate, set learning rate to 5e4, number of training epochs, train for 5 epochs, and even loss computation strategy. Compute loss over all tokens versus compute loss only over output tokens.
Wow, okay. It really takes control.
It does. This self-edit containing these tool specifications and parameter settings is then applied for a lightweight LoRa-based fine-tuning update on the model for that specific task. The performance of the adapted model on a held-out test input for that particular few-shot task then determines the RL reward. So SEAL is essentially learning a meta-strategy, how to best configure its own learning environment for a new, unseen task, based on just a few examples, using a learned tool use policy. It's like a chef who, upon seeing a few new ingredients, automatically knows the best cooking techniques, temperature, and timing for that particular dish.
That's a powerful idea. An LLM learning to act as its own hyperparameter tuner and data augmenter for a specific task without human intervention. Looking at the results in Table 1 for few-shot abstract reasoning, using Llama 3.21b instruct on a curated subset of ARC tasks, it's quite stark. In context learning, ICL, where the model only uses the examples in the prompt, had 0% success.
Zero.
TTT with self-edits, but without prior RL training, so without the model learning how to generate those edits optimally, was 20%. But SEAL's performance jumps to an impressive 72.5% success rate. That's a substantial improvement compared to the baselines, fundamentally transforming the model's ability to generalize from sparse data. However, there's also an Oracle TTT category, representing a human-crafted optimal configuration which achieves a near-perfect 100%.
Right, the theoretical maximum with those tools.
This raises an important question that the paper doesn't fully explore. SEAL significantly boosts performance, but it still doesn't reach that Oracle human-tuned level. What are the specific technical gaps that prevent it from achieving perfection here? Is it a limitation in the search space of self-edits, or something inherent in the current RL training, or perhaps the model's understanding of abstract rules?
That's a crucial observation, and it points directly to the remaining technical challenges and future research directions for SEAL. The gap between SEAL's 72.5% and the Oracle TTT's 100% success rate highlights several potential technical limitations. Firstly, it could indeed be a limitation in the search space of self-edits. While SEAL learns to select from a set of predefined tools and hyperparameters, the expressiveness of those tools might not cover every single optimal configuration or complex multi-step strategy a human expert could devise.
So the toolbox isn't big enough, maybe.
Potentially. The human oracle, leveraging their own intuition and deep understanding of abstract reasoning, might be identifying and applying highly nuanced data transformations or very particular combinations of hyperparameters that aren't yet representable within the current toolset or the natural language instructions the LLM can generate. The abstract reasoning tasks themselves, with their infinite permutations of rules, present a nearly boundless challenge. Secondly, there could be limitations in the current RL training itself. Even with RESTM stability, the optimization landscape for these complex, nested loop systems can be incredibly challenging. The model might get stuck in local optima, meaning it finds good self-edit generation policies, but not the globally optimal ones.
Like finding a tall hill, but not Everest.
Exactly that analogy. The discrete nature of action selection generating specific natural language instructions and tool invocations also makes the policy optimization harder than in continuous action spaces. The number of samples per RL iteration and the overall training time might also constrain the model's ability to thoroughly explore the vast space of possible self-edits. It might be finding good enough strategies quickly, but not exhaustively searching for the absolute best. A third factor might be the inherent difficulty of abstract reasoning for LLMs. Even with optimal self-edits, the underlying Llama 3.21b instruct model, while capable, might still struggle with the truly abstract, non-linguistic pattern recognition required by some ARC tasks. The self-edits help by providing optimal scaffolding, but they can't magically endow the model with a fundamentally different reasoning paradigm it hasn't learned in pre-training.
Okay, so it's likely a mix of things. The tools, the RL search, and the base model's own limits.
Precisely. It's likely a combination of these factors. The bound expressiveness of the self-edit language and tools, the inherent challenges of RL optimization in this complex space, and the foundational inductive biases of the LLM architecture itself when faced with highly abstract, non-textual tasks. Future work would likely need to expand the vocabulary of self-edits and refine the RL training algorithms.
Those are very clear technical avenues for improvement, outlining where the research frontier still lies. Now let's move into Section 4, the path forward. What are the current technical limitations that the present SEAL framework faces, beyond those we've just discussed regarding the Oracle gap, and what's the broader vision for its future?
One of the most significant technical limitations, and a very common challenge across machine learning, is catastrophic forgetting. The paper addresses this directly in Figure 6.
Ah, yes, the classic problem. Learning new things makes you forget old things.
Exactly. The problem is that when you continually update a neural network with new information, these new updates can destructively interfere with previously learned knowledge, causing the model to forget things it knew before. The paper simulates this by sequentially updating SEAL on new passages and then reevaluating its performance on previously learned tasks. The result, as Figure 6 clearly shows, is that performance on earlier tasks gradually declines as the number of new edits increases. While it doesn't completely collapse, the degradation is present and concerning for any system intended for continuous lifelong learning. This indicates that the current SEAL framework, without specific safeguards, is indeed susceptible to catastrophic forgetting.
So how do they propose tackling that?
To mitigate this, the researchers propose several crucial future technical solutions. One is reward shaping, where the RL reward signal is explicitly designed to penalize regressions on earlier tasks.
So you reward learning new stuff, but penalize forgetting old stuff.
Right. So instead of just rewarding new knowledge acquisition, the reward function would also include a term that penalizes any drop in performance on what the model already knows. This would encourage the model to generate self-edits that improve new knowledge without significantly degrading old. Another promising direction is integrating existing continual learning strategies directly into SEAL's update mechanism. Examples include null space constrained edits, which aim to update parameters in a way that doesn't interfere with previously learned representations, or representational superposition, which involves encoding multiple pieces of knowledge within the same set of parameters in a non-interfering way.
That raises an important technical question. How can we technically design a reward signal or an update mechanism that explicitly prioritizes knowledge retention while still allowing for efficient new learning? It seems like a fundamental trade-off that requires a deep understanding of the model's internal representations.
It's precisely a fundamental trade-off, and solving it requires sophisticated technical design. For the reward signal, as mentioned, you can imagine a multi-objective reward function. Instead of just a binary R1 for new task improvement, it could be something like R, alpha new task gain, beta old task loss increase, where alpha and beta are weighting factors.
Balancing learning and remembering.
Exactly. The challenge is tuning alpha and beta effectively and ensuring the old task loss increase is efficiently computable without reevaluating all prior tasks constantly. For the update mechanism, methods like null space constrained edits are fascinating. The technical idea here is to identify the null space of the gradients for previously learned tasks. Think of it like this. Your model's parameters live in a very high-dimensional space.
Okay.
When you learn a new task, the gradients usually point in a direction that changes parameters relevant to that new task, but might also inadvertently change parameters relevant to old tasks. The null space of the old task gradients is a direction in this parameter space where you can make updates without changing the outputs for the old tasks.
Like finding an empty spot on the hard drive.
Kind of like that, yeah. It's like adding new files, but making sure you're writing them in empty spaces or in a way that doesn't overwrite your essential operating system files. By constraining new updates to primarily occur within this null space, you can introduce new knowledge while preserving old. Representational superposition goes a step further by actively encoding new and old knowledge into overlapping, but ideally separable, representations within the same set of parameters. This can involve techniques like sparse activations or clever embedding strategies.
That sounds complex.
It is. These aren't just minor hacks, they are deep architectural and algorithmic modifications. Implementing these would require significant changes to the SFT inner loop, ensuring the gradient updates are performed in a memory-preserving manner. It's a complex, ongoing area of research, and its successful integration into SEAL could unlock true lifelong learning for LLMs.
That makes perfect sense. It's about making space for new knowledge without erasing the old. Beyond catastrophic forgetting and the Oracle gap, what other practical technical limitations does the current SEAL framework face that might hinder its broader adoption or scaling?
Another significant practical limitation is computational overhead. The current TTT, or test time training, reward loop, which is central to how SEAL computes its reward signal, is incredibly computationally expensive.
How expensive are we talking?
Unlike other RL methods used with LLMs, where a reward signal might only require a single model forward pass, SEAL's approach requires a full fine-tuning and inference cycle for each self-edit evaluation. This is critical to understand the bottleneck. The paper states that each self-edit evaluation takes approximately 30-45 seconds on high-end GPUs. When you're sampling multiple self-edits per context and running multiple seeds, this quickly adds up to substantial overhead.
Oof, yeah, that's a lot.
It is. For example, a single round of RESTM training involved 50 contexts, 5 sampled self-edits per context, and 3 runs per completion, resulting in 750 inner loop iterations. This entire process takes roughly 6 hours on 2x H100 GPUs. This poses a significant challenge for scaling up SEAL training for larger models or for more frequent, continuous updates in real-world scenarios. The cost per feedback signal is very high. A third technical limitation is context-dependent evaluation. The current instantiations of SEAL require that every context for adaptation be paired with an explicit downstream task for reward computation.
Like the QA pairs for knowledge incorporation.
Exactly. For knowledge incorporation, passages come with reference question-answer pairs. For few-shot learning, few-shot demonstrations arrive with a held-out query pair. This tight coupling simplifies the reward calculation, but it fundamentally prevents RL training of SEAL from scaling to truly unlabeled corpora. You can't just throw raw web data at it and expect it to figure out how to self-update in a meaningful way.
So how could you get around that?
A promising technical solution to this would be to allow the model to not only generate self-edits, but also generate its own evaluation questions.
Generate its own tests.
Pretty much. For instance, it could draft relevant QA items or synthetic test cases for each passage while the original content is still in context. These model-written queries, potentially cross-referenced or verified for internal consistency, could then provide the necessary immediate supervision for the reinforcement learning process, effectively creating an internal self-sufficient reward signal. This would dramatically broaden SEAL's applicability to general training domains and truly unsupervised learning where external question and answer sets are simply unavailable. It's a meta level of self-sufficiency.
Those are some very clear technical hurdles, especially the computational overhead and the need for explicit evaluation signals. But despite these, the broader technical implications and future vision for SEAL seem immense. The paper mentions the impending data wall, that LLMs will exhaust publicly available human-generated text by maybe 2028. This makes approaches like SEAL incredibly critical, almost a necessity for continued progress, wouldn't you say?
It absolutely does. The data wall projection by Villalobos et al. Is a sobering reality for continued LLM scaling. Once web-scale human-generated corpora are exhausted, the path forward for sustained progress and scaling in LLMs must hinge on a model's capacity to generate its own high-utility training signal. This is where SEAL's vision becomes not just interesting, but necessary. It's a strategic imperative. We can envision a future with dedicated SEAL synthetic data generators. Imagine a specialized SEAL model, perhaps a massive one itself, meta-trained specifically to produce fresh, high-quality pre-training corpora for other LLMs.
So AI training AI.
Essentially, yes. This would involve generating diverse, coherent, and useful text that then serves as the training data for the next generation of foundation models. This would allow future models to scale and achieve greater data efficiency without relying on additional human text, effectively breaking through that data wall and creating a self-sustaining cycle of AI development. Beyond foundational pre-training, consider iterative self-expression and self-refinement in more specific domains. LLMs could ingest new academic papers, complex legal documents, or cutting-edge scientific research. They wouldn't just read them passively, they would generate large quantities of their own explanations, summaries, critical analyses, and implications, using their existing knowledge and reasoning.
Continuously getting smarter on niche topics.
Exactly. This continuous, iterative loop of self-expression and self-refinement could allow models to keep improving their understanding on even rare or highly specialized topics, even in the absence of additional external human supervision. This is truly autonomous knowledge acquisition and distillation.
That's a powerful thought. Models generating their own textbooks, essentially. And how might this synergize with existing advanced reasoning techniques like chain of thought or Cody? We've talked a lot about models generating step-by-step reasoning. How does SEAL fit into that picture? It seems like they could complement each other beautifully.
That's an excellent question, and the synergy between SEAL and chain of thought, Cody, is indeed profound. While modern reasoning models are often trained with RL to generate code traces, which are about inference time reasoning, SEAL is about learning time adaptation. The two could create a truly dynamic, self-improving system.
How so?
For instance, a model might be attempting a complex, multi-step reasoning problem using Cody. If it encounters a novel concept or a logical gap, it might choose to perform a weight update mid-reasoning using a SEAL-generated self-edit. This self-edit could guide it to integrate a new piece of information, refine a specific skill, or even update a logical rule. This would allow it to guide its current reasoning trajectory more effectively, perhaps by learning on the fly. Alternatively, after completing a complex reasoning task, especially if it was a novel one where it had to struggle, the model could use SEAL to distill the key insights, the successful reasoning patterns, or any new factual discoveries directly into its parameters.
So it learns from its thinking process.
Precisely. This would improve future inference by internalizing that learning into its weights, rather than relying solely on in-context examples for every similar new problem. It's about making the Cody process itself more robust, efficient, and informed by continuous self-improvement. It could even learn optimal Cody structures for specific problem types.
And finally, this kind of continuous refinement loop also sounds incredibly promising for building agentic systems, those AI models that operate over extended interactions and adapt dynamically. How could SEAL be foundational there, moving beyond static agents?
For agentic systems, SEAL could be truly foundational. Agents, by their nature, need to incrementally acquire and retain knowledge as they interact with dynamic environments. Our current agentic models often rely on large context windows for memory or on external knowledge bases. While powerful, this doesn't fundamentally change their core parameters or internal beliefs in a persistent way.
SEAL lets them actually change.
Exactly. SEAL supports this crucial behavior by enabling structured self-modification. Imagine an agent that learns from a complex, multi-step interaction. After that interaction, rather than just relying on its current internal state, the agent could synthesize a self-edit summarizing its key learnings, new environmental dynamics observed, or successful strategies. This self-edit would then trigger a lightweight weight update, allowing the agent to refine its internal models of the world, update its knowledge base, or even adjust its behavioral policies based on that recent experience.
So they improve themselves through interaction.
Right. This would enable the agent to develop and evolve its core capabilities over extended periods, constantly aligning its behavior with its accumulated prior experiences. It's a move towards truly autonomous, continually learning agents that don't just act, but improve themselves through their actions. In essence, SEAL demonstrates that large language models need not remain static after their initial pre-training. By learning to generate their own synthetic self-edit data and applying it through lightweight weight updates like LoRa, they can autonomously incorporate new knowledge and adapt to novel tasks. Looking ahead, this framework hints at a future where models are not just intelligent, but autonomously adaptive across diverse tasks and domains, a pivotal step towards more capable and self-sufficient AI.
That's a fantastic summary of a truly groundbreaking framework. We've embarked on a deep dive into SEAL, a cutting-edge framework that lets LLMs generate their own fine-tuning data and adaptation directives. We looked at how it leverages reinforcement learning with a clever rejection sampling approach, RESTIM, to navigate the complexities of non-differentiable rewards and stale data in a stable manner. And we saw how it delivers impressive gains in critical areas like knowledge incorporation and few-shot learning, even outperforming large general-purpose models like GPT 4.1 in generating optimal training data specifically for its own internal updates. We've taken a deep dive into the technical details, showing you how SEAL represents a significant step towards LLMs that don't remain static after pre-training, but continuously evolve and refine their own internal representations. It truly redefines what learning means for these advanced AI systems. So what does this all mean for you as someone invested in understanding the bleeding edge of AI? If LLMs can learn to teach themselves, generating their own optimal training data and refining their own internal parameters, how might this fundamentally change the way we develop and deploy AI in the coming years? What previously impossible applications become feasible when AI can refine its own internal representations and learning strategies in such a sophisticated, autonomous way? It's a truly exciting, perhaps even paradigm-shifting prospect for the future of machine learning.